Hello, everyone. Okay, so let's dive right in. We are on page 44, topic 3.11, spectroscopy and the electromagnetic spectrum. And we've learned about the electromagnetic spectrum. Electromagnetic spectrum's really cool. It's what visible light is. And I just find so uniquely interesting about the electromagnetic spectrum is there's these other things that we know that we recognize, like, oh my goodness, scary gamma radiation. But it's the exact same thing as visible light. It's just got a shorter wavelength. And it's like, oh, really? The microwaves and radio waves. If I just make that wavelength shorter, then all of a sudden it becomes infrared and then visible light and ultraviolet X-rays and then our gamma rays. And there's an energy component that really impacts what these electromagnetic waves, radiation, is used for. So first thing, and we'll dive into calculations in just a moment, but wavelength is inversely proportional to energy. Okay? That like and here's our symbol for wavelength. You'll see this in the equations in just a moment. So wavelength, okay? Wavelength. This has an inversely proportional relationship to energy. So when our wavelengths are really big, that's when our energy is low. And when our wavelengths are really small, that's when our energy is big. And a reminder about wavelength, because it's been a minute. Here's a wave. This wave can keep going. Now, wavelength is the distance between two equivalent points on a wave. Okay? So it's really easy to see peaks and troughs, so we tend to choose those. But you don't have to choose those. But like, here's the peak, and I want to find the equivalent distance. So from peak to peak, or from trough to trough. So this distance from peak to peak, oh, that's the wavelength right there. So there's my wavelength, right? So you can see that the wavelengths are larger here. Here's peak to peak. That's a really big wavelength. But all the way over here, here's peak to peak. And that's really small. So small wavelength, big energy. Big wavelength, low energy. Cool. Atoms and molecules. But we're going to focus on the molecules for a moment. They have the capacity to absorb electromagnetic waves. Okay? And something happens when they do that, and it really depends on how much energy that electromagnetic wave has. Okay? So really cool. First, let's start with lower energy. If a problem says that a molecule absorbs infrared, okay? So I'm going to be, not infrared. We're going to start with microwaves. Lower energy microwaves. So if an AP Chem question says, hey, a molecule absorbed some microwaves, it absorbed a little bit amount of energy. And what happens is that little bit amount of energy makes the molecules rotate. Okay, so like we get vibrational motion, like back and forth, up and down motion, and then we have like rotational motion. Okay, and look at that difference in energy right there, right? Like, oh, it's rotating versus like vibrating, versus like bonds breaking, like jumping to new energy levels. Okay, so when we have a molecule that absorbs the lower energy microwaves, this causes rotational motion in molecules. Beautiful. If we absorb some higher energy infrareds, this causes translational or vibrational motion of molecules. And if molecules absorb ultraviolet or visible, because look, here's our visible, here's our ultraviolet, they're right next to each other. So if it absorbs either of those, what happens is that the electrons in these molecules, okay, so let's draw, here's my protons, we got electrons. So they can jump to higher energy levels, okay, excited states. Like this is enough energy that these electrons can actually jump up to a higher energy level, okay? So these higher energy levels, electrons don't tend to stay there. And then when they jump back down, because we know that lower energy is more stable, they have to lose that energy and they can release the same photon that was absorbed. So if it took a photon in, let's say, the visible light green range to jump from here to here, and then the electron wants to go back to that lower energy level because it's more stable, and it makes that transition back down, that energy doesn't just disappear. It's got to be released, and it's released in the form of that same photon. That's so fascinating. The other thing that can happen is that there can be enough energy that bonds, these chemical bonds, can be broken. And we're not going to spend time diving into this. If you want to later after the AP Chem test, I would be happy to spend that time. But we can cause electrons to jump to what we call them anti-bonding orbitals. And think of it just like as an electron transition, but it's to a place that like wants to break the bond instead of maintain the bond. And so transitions in energy in electrons can actually like break these bonds, okay? Like, oh my goodness, it is so hard to pull these apart. But if it absorbs a photon with enough energy, it can absolutely break that bond, okay? So that's the other thing that can happen. So, review. Low energy microwaves, those cause rotational motion in molecules. Slightly higher infrared, if that's absorbed, then we get translational or vibrational, right? There would two words for the same thing. Motion across, not just like rotational in the same spot, okay? And then the third one is if it absorbs ultraviolet or visible, it can cause electron transitions to higher energy levels, or it can cause transitions that cause bonds to be broken. What I'm going to ask you guys to do, and I'm going to add like your little bit of homework that I want you to think about for a moment, is how can we remind ourselves about this? Like, I want you to think of a way, some kind of like memorization technique to remember that microwaves go with rotational, infrared goes with translational or vibrational, and ultraviolet / visible goes with electron transitions / bonds being broken. So come back to class next time with some way that you are going to have this memorized. And here's why. In true AP Chem fashion, look at all those words and look at all this information. Okay? And so what are we going to do? We're not going to get overwhelmed by this. We are going to jump to the end. I'm not going to read any of this. If I need to, I will come back to this. But I may not need to. And how often have we seen questions where we didn't even need the first like paragraph with a whole bunch of info in there? So I'm skipping this. I'm going right to the question. Which of the following techniques would be best to investigate molecular vibrations? Oh, wait, vibrations? That's microwave. Oh, sorry, as I point to the wrong one. That's infrared. Okay, so rotational is microwave. That's infrared. All right. Oh, answer option A, infrared, right there. Done, answered. I didn't need this. I didn't need this. Okay, so many students, I think I could be wrong, but I think they go into these AP Chem tests and they start reading this information, they get overwhelmed really quickly. And it's usually just packed full of info that they may have forgotten or they simply do not need for the question. And so we can avoid those feelings of being overwhelmed by jumping to the end. Oh, look at this next one. Just another perfect example of what we very often see on these AP Chem questions is that like we're just given so much information, and there's lots of information in these answer options as well. The question is right here. And so let's see what it says. I'm skipping to even the end of the shorter one. Which of the following statements is true about the absorption band in the spectrum? And I go, okay, I know what I'm going after, a true statement, but I'm not sure what the absorption band is. So I'm going to come back up here. Beta carotene is an organic compound with an orange color. The diagram to the left, and it's not even there, my bad, shows the ultraviolet spectrum. Guess what? We don't need that diagram to the left because it's told us ultraviolet spectrum. So, what's ultraviolet? Electron transitions / bonds breaking. So they could mention electron state transitions, or they could be talking about breaking bonds. So let's see what we got going on here. A, the absorption band between 250 and 320 nanometers is due to transitions in electron energy levels, and the absorption band between 380 and 520 is due to transition in molecular vibrations. B, the absorption band between 250 and 320 is due to transitions in molecular vibrations, and the absorption band between 380 and 520 is due to transitions in molecular rotation levels. C, the two main absorption bands are associated with transitions in electronic energy levels. The band in the region corresponding to shorter wavelengths show a lower absorbance than the band in the region corresponding to the longer wavelengths. I'm most interested in this one right now, but I'm going to come back and see. So here's what I'm doing. With A, I really honed in on transition in electron energy levels because I definitely am like, yep, that's ultraviolet. But then it went on and it said also vibrational. I go, oh no, that doesn't happen with ultraviolet, so that can't be it. Same here, it talked about vibrational, and I go, nope, it can't be it. C only talked about electron energy levels, so I go, yeah, maybe. And then D, the two main absorption bands are associated with transitions in molecular vibrational levels. Nope, not vibrational. Correct answer is C. So we're just trying to pull out the important bits of information and drawing connections between that important information because it's really easy to get overwhelmed by how much is in front of us, especially with these questions with lots of info. Alrighty, now we're jumping to 3.12, and this is properties of photons. And I'm going to tell you right now, the main things that you need to be able to do is you need to be able to work and rearrange this equation and calculate with it, and then same Z's with the energy one, okay? So when we have these like goals that we're setting for us, like this is the goal that I want you to achieve, is know these equations, understand them in a way that you can apply them and calculate with them. And both these equations are for photons, okay? So, we recognize this symbol because we talked about it earlier. This is wavelength. Hey, let's look at our reference guide so you know exactly how this is going to look for you when you take the test. Oh, it tells us. That's so wonderful. So do you see? Oh, just a reminder in case you forget, this symbol represents wavelength. The V actually represents frequency. E is energy, okay? And then here, right across from it, are those two equations that you're going to be expected to use and calculate. Energy is equal to H times by V. Okay, hold on. Boop. V is frequency. H is Planck's constant. Great. Okay, back over. C is equal to wavelength times by frequency. But what's C again? Boop. It's right there. It's the speed of light. And so do you see how it's just right directly across from it? So these equations correlate with those, and then these equations correlate with these. Okay. Alrighty. So we know that this is wavelength. We've talked about what wavelength is, peak to peak, trough to trough. And this is a distance, and this is important, everyone, so listen carefully. We need wavelength to be in units of meters, okay? So our units are meters, lowercase m. So if it's not in meters, if it's in nanometers, then we need to change that. And look, here is nano. Nano means times 10 to the negative 9. So if I have a problem, just like down here, the wavelength is 545 nanometers. So my wavelength is 545, and I'm going to change this. Instead of nanometers, I want it to be meters, so I'm going to go times 10 to the negative 9, because that's what nano means. And now it's just meters. Great. So I need you to convert it to units of meters. Wavelength is equal to frequency. So now we know that this scripty V here is frequency. Okay. Frequency is how many waves pass in a given amount of time, and that given amount of time is seconds for us. But like, imagine with me. Let's say we're at the beach, we walk out to the end of the dock, and we're watching waves come in and they're hitting the dock, okay? The distance between the tops of the waves is wavelength. But what frequency would be is like, okay, I start my timer, click, and I'm counting how many waves hit the dock in 1 minute. Oh, there was 12 waves that hit the dock in 1 minute. That would be a frequency of 12 per minute. Okay? So here, instead of per minute, it's going to be per second. And that's what the units are. Per second. There's other ways that you could see this. Remember how it's raised to the -1, and these mean exactly the same thing. So this is per second. The other way that you could see this, per second is the same as hertz. And I'm going to highly suggest that when you see hertz, that you change it to the per second, because it can help you see what units you're supposed to end with. Okay. Great. Here's a really common rearrangement of this, but you guys are strong in your algebra, so we can clearly see that if we're solving for frequency, we would just divide by wavelength, or if we were solving for wavelength, then we would divide by frequency. Okay. Speed of light is a constant, and on our paper, so let's do speed of light. And on our paper, it tells us that we are using 2.998 times by 10 to the 8th meters per second. Meters per second. Or meters per second. Okay, mean exactly the same thing. Beautiful. Let's practice. Find the frequency. Okay, find the frequency of a green light that has that wavelength. Great. We also know the speed of light because it's constant, so I'm going to add this to my list of knowns and unknowns. Okay, so I recognize that I need this equation. And on my reference sheet, it says speed of light is equal to wavelength times by frequency. And I'm solving for frequency. This is a great equation to choose because the thing I'm looking for, I don't have my information on, but I know everything else. I know the wavelength, reminder, wavelength has to be in meters, and I know the speed of light. So then if I want to isolate this, I would divide by wavelength. Speed of light divided by wavelength equals frequency. I, at this point, would not rewrite this with the numbers in there because I already did my list of knowns and unknowns. So this is perfect work that we would want to see on this AP Chem test. So I'm just plugging it in now because I've shown that it's going to be speed of light, which is 2.998 times by 10 to the 8th. And I am dividing that by wavelength in meters. 545 times 10 to the negative 9. Cool number. Sig figs, though. This was 3 sig figs. This was 4 sig figs, so I'm going to go with 3 sig figs. So my final answer for frequency is 5.50 times 10 to the 14th. Okay. Units. Okay. The fastest way to go about this, and unfortunately we do value that time component on these time tests, is to remember to memorize that frequency has units of inverse seconds, however you're choosing to write that, or hertz, right? If you've forgotten, though, then you can do a quick unit analysis. You can say speed of light is meters per second. I am dividing that by wavelength, which is meters. I'm going to put this over 1 because now it's really, if they're both fractions, it makes it really easy for us to go, oh, dividing by a fraction is the same as multiplying by the reciprocal. And now that they're multiplied, it's like it's a big fraction. Meters cancels, it's on the top and the bottom, and so we ended with, look, inverse seconds. Another way of writing this is seconds to the minus 1. Okay, great. Same idea, energy. So we have these written down here. Just remember, do not forget. So like we have right here, E is energy, and it has units of joule, capital J, joules. H is Planck's constant. Ooh, let's update this number. Just update it. Because I want you to use the number that's on your reference guide. And it's really close, but it's not quite the same. 6.626 times 10 to the negative 34. 6.626 times 10 to the negative 34 joules seconds, joule seconds. Great. V is frequency. Okay. Let's do an example where you have to use this equation. The complete photoelectron spectrum of an element in its ground state is represented above. Calculate the wavelength. Okay, so we're solving for wavelength. In meters of electromagnetic radiation needed to remove an electron from the valence shell of an atom of the element. Okay. Finding energy. This is where binding energy is the highest. This is where it's the lowest. And remember how the closer those electrons are to the nucleus, the higher the binding energy is. So these are the electrons closest. These are the electrons furthest away. So we know that those are valence electrons. We could also have some here, but they're focusing on this. And it would be interesting to see, because this would be a 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Oh, nice. So these ones are just the valence electrons. We didn't have like a prior one over here. Beautiful. That's our energy. So we're solving for wavelength. We know energy is 0.980 times 10 to the negative 18 joules. There's a couple other things that we know. We know Planck's constant, 6.626 times 10 to the negative 34 joule seconds. We know the speed of light, 2.998 times by 10 to the 8 meters per second. Okay. So, I'm sure some of us might be seeing where our connections are here, but sometimes it's not so obvious. Look at these two equations. We know speed of light equals wavelength times by frequency, and we know energy is Planck's constant times by frequency. I'm solving for wavelength. I know the speed of light, but I don't, look, frequency is not on my list. I don't have my frequency. It's missing. But if I come over here, I know energy. I know Planck's constant. Oh, so I could solve for frequency and I could plug it in right there. We could numerically plug it in, meaning like I actually calculate it and then I plug it into this equation. That's the most commonly used method. Or you could rearrange the equation for frequency and plug it in. Okay? Let's start with how most students do this. So I want to solve for frequency so I can use it right here. So I'm going to divide by Planck's constant. So if I take my energy and I divide it by Planck's constant, then I will get my frequency. Okay. Energy is 0.98 times by 10 raised to the negative 18th. I'm dividing that by Planck's constant, 6.626 times 10 to the negative 34. So that's my answer for frequency. I do not want to round for sig figs right here. That'd be intermediate rounding. It can cause some errors. So I'm going to write a whole bunch of digits. 1.4790 times by 10 to the 15th. Frequency, inverse seconds. Okay. Now that I do know frequency, right, 1.4790 times 10 to the 15 inverse seconds. Oh, great. I now know this. So I can rearrange and solve for wavelength. Speed of light divided by that frequency number I just calculated will give me my wavelength. Notice that I'm putting these in parentheses so that we don't run into any order of operation errors by our calculator. So I'm going to now take the speed of light, 2.998 times by 10 to the 8th, and I'm going to divide that by this frequency number. Grab it from up above, so we're using the longest number possible. We're getting as many of those digits as we can. Your calculator may have given this to you in scientific notation. Mine gave it to me in standard. Your calculator might be saying right now, let's see, 1, 2, 3, 4, 5, 6, 7. Yours might be saying 2.0, etc., times by 10 to the negative 7. Now I'm curious how it will read it there. Yeah, just like that. Okay. So either one's fine. 0.123456203, and this is wavelength, so it's in meters. Or we could say 2.03 times by 10 to the negative 7 meters. Okay, let's check sig figs. This is what's so great about like our list of knowns and unknowns. We know that this one was in between, but I use these other numbers. Leading zeros are not significant, so that'd be 3 sig figs, 4 sig figs, 4 sig figs. Oh, so 3 sig figs it is. Oh, and it's already in 3 sig figs. Nice. Again, the other option is taking this and plugging it into this equation, and that can be a little confusing because then what we got is like a double fraction where it's like e divided by h, because that's the same thing as frequency. So it's like here, plugging that in equals frequency. Okay, good work everyone. Did I get units on that? Yep, sure did. Meters. Okay, I will see you all in class. I have some cool demos that I'll show you, so it should be a good day. See you then.